Hello and welcome back. Let's talk about some rates of change and hop into some related rates. So, rates of change. What is a rate of change? Well, a rate of change is a derivative. We can remember that from this simple graph that I drew when we first started talking about derivatives. I really like this graph for some reason. I always draw it. But we're starting to talk about applications of derivatives, so we need to know what does this mean. So let's say this was a distance time graph, and I use R because now that we're into calculus, we don't want to use D again because we use D a lot for a small change in something. So R is our distance traveled and T is our time. And what if we wanted to find out the instantaneous velocity at this point? Well, it would be a tangent line. It would be dr dt at that point. So, let's talk about what some rates of change mean. We'll also do a really fun one that I found very interesting when I first learned it. So first we have distance traveled, r. And you can take the derivative of a vector. It's very easy. For now, we'll just talk about what they mean. dr dt equals velocity. And those could be vectors or not. If you take the derivative of a vector, you're going to get a vector. We won't get into that too much, but just keep that in mind because displacement and velocity are both vectors. Another one, let's take dv dt. Well, we know that the time rate of change of velocity is acceleration. So that is acceleration. Let's take a moment to talk about this notation for derivatives. We can notice that acceleration is the derivative of velocity, which is the derivative of displacement. So we could also write it as acceleration is equal to d squared over dt squared of of r. And that's what we write for a double derivative. Triple derivative, it would just be 3's and so on and so forth. So, after that, let's talk about some other things. We have a change, and you might know this if you are in physics. A change in momentum is equal to force. You have to apply force to change momentum. And this is interesting because we know the formula, F equals ma, or I'm not going to write that down yet, but we know P equals mv, mass times velocity. Mass cannot change. You can't change the mass of yourself. You could, but not really. The mass would still exist. You can't destroy or create matter. So, if we take F equals dp, or no, sorry, not dp dt, d dt of what does P equal? mv. Well, if we can't change m, it's a constant, so we can take it out front of it. So we get it equals m dv dt. What's dv dt? ma. And that is exactly how Newton derived his second law formula. That's some interesting stuff. So let's apply this to some related rates. I have a great problem for us. Everybody has one of these problems in any situation, whether it be on an assignment, a test, an exam. Let's talk about it. We have a ladder, and it's leaning against a wall. Here's our ladder. This is our ladder. The ladder is 13 feet. This is the wall. This is the ground. There's no friction. That'd make it very complicated. We're not going to talk about friction. But the ladder is sliding down the wall at some rate. But that means it's also sliding this way. And we know how it's sliding this way. It's 2 feet per second. And what we want to know is how fast is this changing? Let's talk about it. Well, we can call this dy dt. We can call this dx dt, because that's how fast our x-coordinate is changing. Now, how are we going to relate y and x, or dy dt and dx dt? Well, that's easy. I forgot to add this part. It's a right triangle. So, the real question here, and I forgot this part, is at a certain amount of seconds, or no, not seconds, sorry, at 5 feet, this thing is at 5 feet. It's 5 feet away from the wall. How fast is this going down? Because this is going to change based on how this is changing. So when this is changing this is constant, this is going to change. So when this is changing at 2 feet per second, at 5 feet, how fast is this one changing? Let's figure it out. So we know x squared plus y squared equals 13 squared, right? So let's take the derivative of each side with respect to t. X squared plus y squared equals, well, the derivative of any constant is just 0. There we go. D dt of x squared, we're going to have to use the chain rule there, implicit differentiation. We've got 2x dx dt plus, same thing with y, we're just going to get the same thing just in terms of y, 2y dy dt equals 0. This is what we actually call a differential equation. Don't worry about that, but if you plan on going farther in mathematics, you will have to deal with those, maybe solving that. But for now, we know we can solve here. Well, x is 5 feet, so we have 2 times 5, that's 10 feet. Y, well, we can find y here. We have 25 plus y squared equals 169. It's going to give us what? Y squared, or y equals root 144, which is just 12. So we have 2 times 12. We know dx dt is 2 feet per second. I'm going to switch this over to the other side. We've got negative 2 times y, which is 12, so that's 24 feet, times dy dt. Dy dt is how fast it's sliding down here. Now, let's take this. This would be, we're going to cancel our feet here. We get 20 feet per second divided by 24, or sorry, negative 24, this is all negative, equals dy dt. This is, if we divide by 4 here, this is equal to negative 5 over 6 feet per second is dy over dt. Not too bad. Now there's going to be harder questions and stuff, but I hope this can help you with the fundamentals of it. And we can also make sure that our answer makes sense. Our answer is negative. Well, that's because it's sliding down. So that's great that we got that. Anyways, that's rates of change. That's related rates. Very productive video. Lots of applications for this in the real world. You'll never go about your daily life the same after watching this video, I promise you. So, Good luck with your calculus.